contraction. We've done the signal to the muscle to tell it to contract. Now we're going to look at how do we get oxygen and nutrition to the muscle for energy and contraction. All right. As with the other chapters, the first part of this chapter is really an AFP review. So I'm going to go through it relatively quickly. If I'm going too fast for anybody, give me a yell. Okay, but it should be review. So hopefully we can get through the first bit pretty quick. All right. You want to make sure that you have a good idea of the pulmonary and the peripheral circulations, all right, and the structure of the heart, not because there'll be a heart that you have to label on the exam, but because if you don't understand the layout and structure, then the adaptations and things become more tricky, all right? If you know the layout properly, then the adaptations are a lot more reasonable, right? They make more sense. So, here's our structure and our organization. So this should not be new. Let's turn that front light. I've got to get them to come in and focus this properly because I can't work out how to do it. All right, so this should look familiar, hopefully. Okay, remember that we've got blood coming into the heart, to the right side of the heart, okay, to the right atrium, from the right atrium to the right ventricle, out to the lungs, back from the lungs to the left atrium, down into the left ventricle, out through the aorta, off around the body. All right, so make sure that you know your sequence and your directions there. And one of the things that it's important to understand is that the heart is a muscle, although the structure of that muscle is a little bit different to our skeletal muscle that we were looking at. But it does not get its oxygen and nutrition from the blood that is flowing through it, through the inside. It has its own set of arteries that wrap around the outside of the heart, of the muscle, and it gets its oxygen and nutrition from those. All right, the main ones, largest ones are the left and the right coronary, and then they branch off and spread all over the surface to deliver glucose and oxygen. All right, so if we have blockages in any of these, then that's when we have problems with ischemia, because the muscle, the other side of the blockage, isn't receiving the nutrition that it needs. All right. So how does the heart contract? Right? It does receive information from the central nervous system, but it also has the ability to control its own beat, or at least to initiate its own beating. Right? So when we look at the cardiac cycle, in lab last week we were looking at blood pressure, and we said the high number is the systolic pressure. All right, systole is the contraction phase of the cycle. So when the heart, the atria, and then the ventricles are contracting, because they're contracting hard, that lifts the pressure in the system. All right, so the high number is the systolic pressure, and diastole is the relaxation phase. So then after contracting and squeezing the blood out, it has to relax to allow blood to pour back in again. So the diastolic pressure is the lower number. Okay. So we have this intrinsic control, and it's called autorhythmicity, which I don't know that word. It's too difficult to say, right? The ability to initiate its own impulse, its own electrical signal. And that occurs from a specialized set of cells that are located at the rear, at the top of the right atria. Okay? And it's called the sinoatrial node. So it's got this specialized cells, and they act like a pacemaker. They're able to initiate an electrical signal that runs across the inside surface of the muscle tissue. Okay. So we initiate an action potential that spreads across to the top of the right ventricle. And there's another little specialized set of nodes called the AV node, atrioventricular node. And they're responsible for holding on to that signal for a minute amount of time. All right? And that's important because if the atria and the ventricles were contracting at the same time, where would the blood go? Right? So the blood flows into the atria contracts and it flows into the ventricle, and then the ventricle contracts and it flows out of the heart. So it's like a slight delay between the contraction at the top and the contraction at the bottom. So if you ever watch a documentary on heart surgery or something like that, you'll see that the whole thing doesn't contract at the same time. There's like this wave of contraction across the heart. Okay? So the AV node is responsible for hanging on to that electrical signal for about 1/10 of a second and then initiating it off across the ventricle. And it's able to use some specialized fibers called Purkinje fibers to speed up the transmission of the signal down to the bottom of the atria, because you don't want the bottom of the ventricle, rather. You don't want the bottom contracting a lot later than the top of the ventricle, right? So the Purkinje fibers are able to transmit the impulse very, very quickly. Okay. So the SA node, the pacemaker, stimulates a heartbeat that is about 100 beats per minute. Okay? And so while we're sitting here at rest, our heart rate is not 100 beats per minute. Okay? So that means that there has to be something else influencing heart rate. Okay? So the SA node is the intrinsic control of heartbeat, about 100 beats per minute. But we also have some external influences. Okay? So the extrinsic control is information from the central nervous system, mostly. We've also got some hormonal influence as well. Okay. So the parasympathetic system, remember, is our rest and digest system, all right, from the previous chapter. So the parasympathetic system brings information to slow the heart rate down from the 100 beats per minute that it's set at. Okay? The sympathetic system is our fight or flight. Okay? So when the sympathetic system is stimulating the heart, it increases heart rate. Right? So at rest then, you've got parasympathetic stimulation is predominant because your heart rate is way lower than 100 beats per minute. Right? When we're exercising and our heart rate is 140 or whatever on your heart rate monitor, then the sympathetic system is predominant because it's raising heart rate to allow for more blood to be pumped to the muscles so that we can make ATP and see lots of muscle contraction. So at any one time, our heart rate is this kind of balance between parasympathetic and sympathetic. All right? If I'm lower than 100, my parasympathetic is predominant. When I'm rising up from that lower rate, it's because initially I've switched off the parasympathetic. So when your heartbeat first starts to rise, that isn't because sympathetic kicks in. Initially, I have to turn off the parasympathetic. It starts to rise, and then the sympathetic kicks in and it keeps rising. Okay? When we talk about the effect of exercise on heart rate, and we say that a lower resting heart rate is healthy, right? Low heart rate is called bradycardia. So, especially if it's less than 60 beats per minute. So, Mason, your resting heart rate is bradycardia, right? But her resting heart rate being below 60 is because of all the exercise and the kind of activity that she does, right? Bradycardia can also be an indicator that there's something wrong with the heart, with the stimulation, all right? And so if you have a really low resting heart rate but you don't exercise, that would be a red flag to a doctor to get some more tests run, okay? So when we looked at skeletal muscle, we said that depending on the fiber type and the activity that we were training it for, we were either looking for more synchronicity in contraction or less synchronicity if it's a type 1 fiber and I'm doing endurance work. Well, when I look at the heart muscle, it's a slightly different picture. All right, because the cells are not long and lying adjacent to each other. They're like little cubes and they're all stacked around each other. And we don't want the delay that we have with a skeletal muscle where we said that all that, the endocardium and the pericardium and the ecto, that was there to prevent the signal from one fiber transferring to the fiber next door. That's exactly what we want in the heart though, right? We want all the fibers to be stimulated at about the same time. So we have these intercalated discs. If the chapter, I can't remember, but if the chapter goes into a lot of detail about how these work, don't worry about it unless you want to, all right? Because this is quite different to the skeletal muscle and it's a little bit more complicated in my view, and I don't want you to get them muddled up. right? I'd rather that we learn the skeletal system first, and then if we had the opportunity to do another class, then we could look at the action potential in the heart muscle. Right? So I'm going to skip that point for a minute. I'll come back to that. When we look at the fibers in the heart, they are very good at using oxygen, okay? Which is a good thing, right? Because we don't want our heart to get worn out and fatigued. So we want it to be able to keep beating continuously for many, many years, okay? So we see very high numbers of mitochondria within a myocardial cell. As we looked at in that picture before, there's an extensive capillary and arterial system wrapping around to deliver blood and remove carbon dioxide. And so these muscle cells use aerobic energy for contraction, right? So they're similar to our type 1 fibers when we look at skeletal muscle, but they're not exactly the same. But they work more like a type 1 fiber. And there's only that one fiber type when we look at myocardium. We don't have different types. Come on here. Okay. All right. So, left side of the heart versus right side of the heart. Okay? The right side of the heart receives venous blood from the body into the right atria. When it contracts, it squeezes through to the right ventricle. When it contracts, it is pushed out to the lungs, which sit right here. Okay? Comes back from the lungs to the left side of the heart, to the left aorta, into the left ventricle, out through the aorta to the entire body. So which side of the heart has to do the most amount of work? Right, left? Left, right? Because it's got to pump blood through the entire body, all the way down to your toes, right? So when you look at the heart, not surprisingly, okay, the left side of the heart has a thicker wall and more muscle mass than the right side of the heart, right? It's just like doing dumbbell curls with a 2-pound weight and a 10-pound weight, right? Which bicep is going to be bigger and stronger, okay? So because the left side of the heart does more work, it is thicker and stronger than the right side of the heart. Make sense? So, knowing that, okay, then what we see with aerobic training is even more thickening of the left ventricle wall, all right, and an increase in the weight, in the mass of the left ventricle, okay? We also see that adaptation in people who are chronically hypertensive, all right, because when you have to squeeze the blood out of the aorta. It has to go through the aortic valve. And the valve is placed so that the valve is like this. So the pressure in the system is pushing against the back side of the valve. So the left ventricle has to push hard enough to overcome the pressure and push the blood out through the valve. So the higher the pressure in the system, the harder the left ventricle has to work to get the blood through the aortic valve. So when you are chronically hypertensive, you are consistently making your heart work way, way harder than it should be working. All right? And so, because it's working hard, we see similar adaptations. All right? So again, it's a red flag to a cardiologist. All right? If you go in and you've got thickening of the left ventricle wall, which they can look for with equipment, right? We can't tell, but in a hospital, and you say, "Oh no, I don't ever go walking, or I don't do anything." They're going to go, "Oh, let's take your blood pressure," right? So does that make sense? All right. So that pressure in the system causes the left ventricle to have to work much harder. All right. It's also why we don't want people who are hypertensive to do weight training. Okay? Because when I push a weight, right, imagine what you see when you see someone pushing a big weight, right? The face goes red, the veins bulge out, right? Because pushing weight, you basically hold your breath and it increases the pressure in the system dramatically. Okay? So that will come back when we look at training plans. Okay? You have to remember this idea of pressure in the system. ECG, we don't have anything about ECG on the exam. But I want to show you this because if you don't know what the blips on an ECG stand for, then they kind of help you get the cardiac cycle into your head as well. Okay? So if I could read my notes. All right. So, the first little blip here is called the P wave. But what's important to us is that that little blip is the depolarization of the atria. So when they're depolarizing, they're contracting. Okay? Remember our resting membrane potential. We open the ion gates. We change the potential across the membrane. We have an action potential, and then we have to go back to the resting. We have repolarization to go back to the resting membrane potential. Right? So that little blip is atrial contraction. Okay? Then you have a rest. That is the AV node sitting on the impulse while the atria contract and get the blood into the, right? Then we have the ventricle contraction. Because the ventricles are much bigger and stronger, the contraction wave is much higher, okay? And also because that wave is so high, at the same time as they're depolarizing, the atria are repolarizing, but it gets lost in this big spike. So we don't see the relaxation phase of the atria, all right? That's the ventricles contracting. ST segment, and then that blip is the ventricles repolarizing. And then we just go again. Right? So we would have that blip for this, but it gets lost in here. Okay? Cardiologists will use that ST segment for clinical diagnosis. Okay? If you're doing a stress test, so even Dr. Barlow, when you're doing a stress test in the lab and you've got the monitors on and he's watching your ECG, if this ST segment is not pretty level, he's going to pull you off the stress test. All right? Because that's one of the indicators for damage in the heart muscle. If that's too low, then that would indicate damage, and then they would pull you off the test. All right? And send you for further assessment. So as I say, the ECG information isn't on the exam, but I think for me, understanding what the ECG is representing helps me get my cardiac cycle into sync in my head. So the next piece of the pie that we need to know is all the terminology that surrounds cardiac function, okay? So the first measure that we have is called cardiac output, and that is when you look in a book or at a research paper, cardiac output is represented by Q. I have no idea why they use Q for cardiac output. And if they have put a dot over the top of it, that means per minute. All right? So cardiac output is the amount of blood that is squished out of the heart per minute. So I can calculate that if I know what my heart rate per minute is and how much blood is pushed out per beat. Okay? So the equation Q equals heart rate times stroke volume. So Q is how much blood leaves per minute. Heart rate is beats per minute. And stroke volume is blood per beat. So mathematically the beats cancel out and I have blood per minute. So again, depending on, I think that's easier to remember, but if you don't like the equation, then cardiac output is the amount of blood pumped per minute. Stroke volume is the amount of blood pumped per contraction, so per beat. Stroke volume is the amount of blood per beat, right, per contraction. And so we have these two horrible terms. Okay? Remember that diastole is relaxation. systolic is contraction, all right? So, the end diastolic volume, all that means is how much blood is there in the heart at the end of relaxation. Alright, so don't let the long fancy term get you nervous. All it means, alright, we're looking at relaxation. How much blood is there in the heart at the end of the relaxation phase? End systolic volume then is how much blood is left in the heart at the end of the contraction phase. You never get 100% of the blood out. There's always some left. Okay? So stroke volume is just end diastolic volume minus end systolic volume.
You said SV is what?
Stroke volume.
But like what's the equation?
Oh, EDV minus ESV. So you could say stroke volume equals EDV minus ESV. So at rest, our Q, right? How much blood do I pump out per minute when I'm just sitting here not doing very much? Okay? It's about 4.5 to 5 liters per minute, depending upon whether you're a great big large guy or a little tiny girl. Okay? So if you think no one's got a liter bottle with them, that's not a liter, I don't think. That's 20 ounces. So that's not quite a liter. And your pump, sorry?
Is it ready to? Yeah.
Yeah. That's a liter? Okay, that's a liter. And while you're sitting here not doing anything, your heart is pumping 5 of those per minute. Right? Note number 1. We have to take better care of our heart because it works very, very hard your entire life, every second. Right? When you are exercising hard, particularly if you're doing aerobic work, that can be anywhere from 20 to 40 liters per minute. Right? That's how hard your heart is working. Okay? Thank you, that was useful. All right? So, bear that in mind next time you want to eat that 3rd piece of fried chicken. Right? Stop at 2. Now, we're going to talk a lot over the rest of the semester about the differences between someone who is regularly physically active versus someone who is relatively sedentary, all right? And there are usually quite large differences between those two populations. However, when we look at resting Q at this 5 liters, all right, whether I am fit or unfit, whether I am large or I am tiny, when I'm sitting here doing very little work, the amount of blood I need to do very little work is exactly the same whether I'm fit or not fit, because I'm not doing any work right now. Does that make sense? All right, so let me say that again. When you are at rest, this isn't moving, all right? There's no difference in Q between someone who is sedentary and someone who is highly trained. Well, highly trained there would probably be a little bit, but between someone who is regularly active and someone who is sedentary, there wouldn't be very much difference in Q. Because the amount of blood that I need to do very little work is the same for everybody, right? If my intensity is 2, I need X amount of blood to deal with that intensity. If my intensity is 50, now we've got a difference. So how much oxygen, how much carbohydrate, how much fat my muscles need to do very little work is the same whether I'm trained or I'm not trained. Right? So, having said that, here's where the difference is. Okay? Because we said that if we train hard, our resting heart rate is lower. Yes? So, if I am the trained person, I have if I am the untrained person, Q doesn't change. Q's the same. But in the untrained person, we achieve that Q, that 5 liters, like that. Okay. So the fitter I am, the less work my heart has to do, because it's able to push out more blood per beat to achieve the same work rate. All right, does that make sense? Ish. So if I do aerobic work, we see an increase in this stroke volume, all right? The increase in stroke volume occurs for a couple of reasons. The most obvious one, right, is that we see a change in end diastolic volume. So at the end of the relaxation phase, in someone who does a lot of aerobic work, they've got more blood filling up their heart than someone who is sedentary. Okay. In some people, we also see, because the heart gets stronger and thicker, we see a decrease in end systolic volume, because it can contract harder and so it squirts more blood out during the contraction. So now, the same equation gives me a bigger SV. And if I have a bigger SV, but I'm at rest and my Q is going to be 5, then my heart rate comes down. So if we graph stroke volume, stroke volume plateaus at around 40 to 50% intensity. So stroke volume goes up and then plateaus. Okay? Heart rate goes up until you drop on your face, right? So Q goes up and then keeps going up, but at a lesser incline because stroke volume plateau. So heart rate increases with increasing workload because Q has to get larger in order to provide enough blood to the muscles to get oxygen and carbs and fats to the muscle, right? So because stroke volume plateaus, we have to rely on the fact that heart rate just keeps going up as I work harder. That's why heart rate is such a good measure for training intensity, right? Because if I'm working harder, my heart rate goes up. If I'm working less, my heart rate goes down. So we have another little element that helps out with lowering our ESV and systolic volume, all right? And it's a little bit like the elastic band effect that we talked about in the skeletal muscle, all right? It's called the Frank-Starling mechanism. So when I put more blood into the heart and I stretch the heart muscle, as I contract, it rebounds and it adds power to the contraction. And so that's another, when you look at the book, you'll see that term, the Frank-Starling mechanism. It's kind of like that rubber band mechanism, right? But it helps, it feeds into this idea that we get a lower ESV with training. Because my EDV is higher, I put a bigger stretch on the wall, and then as it contracts, it rebounds more strongly. Who knew there was all that stuff going on in your heart when you're running around the track, eh? All right, so we'll stop there, and we'll pick up with blood flow on Wednesday.